Okay, we want to find a polynomial to fit this graph. Well, we know that there's zeros at x equals -1, 1, and 3. -1, 1, and 3. And you can see where I've implicitly marked off the x and the y-axis. These are unit markings. And y-intercept at y equals 1. Now, what function could possibly have these zeros? Because that's the easiest part to determine. Well, we could get a 0 at x equals -1 by a factor x plus 1. We get zeros at 1 and 3 by factors x minus 1 and x minus 3. So we could try, could y equal this? Okay, well, let's see what the graph of this function would be. Okay, graph of this function would have zeros right where they ought to be. Okay, at -1, 1, and 3. So we have zeros here, here, and here. Now, end behavior. What's the end behavior of this proposed function? Well, if x is a large positive number, this is a large positive, this is a large positive, this is a large positive. So when we multiply them together, we get a humongous positive number. Okay, so well, let's see. That means that on this end, the function has to take off rapidly in this direction. Now, if x is a large negative number, these are all going to be large negative numbers, so we're going to have 3 large negative numbers. Well, 3 negatives multiplied together give us a negative. And the result's going to again be humongous. So here's our end behavior over here. That doesn't match the end behavior of this function. The end behavior here is this and this. We approach large negative numbers on both ends. Here we're stuck with approaching large values in opposite directions on the two ends, not even in the same direction. So something is wrong here. So the model doesn't quite fit. Now, let's try. First of all, also the intercept. The y-intercept is what? It's 3 times 1. Y-intercept is plus 3. Okay, well, that could be possible, but of course the intercept that we want is plus 1. Still, if we had a y-intercept of plus 3, we could conceivably take 1/3 of that function, which would reduce all the y values by a factor of 3. So we put a 1/3 out in front here, and we get that y-intercept down to plus 1. So if we took 1/3 of this, the x-intercepts stay the same, but the y-intercept is now 1. As you can verify by multiplying these out, you get 3. 1/3 of that is 1. So we can always put a number in front here. Now, we still have the problem, though, that the end behavior is wrong. So what are we missing? Well, a hint comes from the fact that this function goes through this 0, it goes through this 0, but it just touches this 0. The only way that can happen, well, I won't say the only way, the most likely way for that to happen is for the factor that gives you this 0, which is the x minus 1. It gives us a 0 at x equals 1, where the function kind of acts like a parabola with a vertex on the axis. It doesn't pass through the axis. It acts like a parabola with this vertex. That 0, again, which corresponds to the x minus 1 factor, occurs because the x minus 1 factor is squared. Okay? If it's like this, these are linear factors. X plus 1, x minus 1, x minus 3 are linear expressions in x. If you set y equal to any one of these, you have a linear function. Okay, if we square this x minus 1, we now have a quadratic function, which is compatible with the idea of having a vertex and touching the axis only at that vertex. So we make the second change, which is to square that x minus 1. Okay, well, let's not do this. Let's do it separately. Okay, the end behavior is still very wrong. Okay, we observe the 0 at 1, 0 is from the factor x minus 1 and acts like the vertex of a parabola. The graph has that shape here. So use x minus 1 quantity squared. Now our function is y equals 1/3 of x plus 1 times x minus 1 quantity squared times x minus 3. The end behavior is now exactly what we want, in the sense that both ends act the same. If x is a large positive number, well, this is going to be positive, everything's going to be positive, so we're still going to have upward end behavior on this end. If x is a large negative number, well, this is negative and this is negative, and of course any square is positive, so we have a positive times a couple of negatives, that's positive. Okay, end behavior is the same on both ends. This is a big improvement. But the end behavior is in the wrong direction. The end behavior is up instead of down. So how are we going to revise our function to accommodate that? Okay. The end behavior is up, not down. That would mean that you have to approach this 0 from above, and this 0 from below, and this 0, this 0 from below, it'll turn around, then this one goes up. So it'd be kind of an upside down picture of this, and your y-intercept wouldn't match. Your y-intercept would have to be down here. If you're coming down and through this 0, then to get back to this 0, you got to go through the y-axis on the negative side. So how do we get around that? Well, let's move over to the approach we used in class. This is directly from class. We conclude that f of x is a times x minus negative 1, of course that's x plus 1, times x minus 1 squared times x minus 3. From the fact that the graph goes linearly through this 0 and this 0, we expect these are first powers, and acts like a parabola here, we expect this is a second power. We have the fact that f of 0 equals 1. It's not negative, it's positive. Okay, well, if f of 0 equals 1, and if f of x is a multiple of these three factors, then f of 0 is, okay, that factor a multiplied by, of course, 0 plus 1, 0 minus 1, 0 minus 3. and that gives you negative 3a. Now, if f of 0 equals 1 and f of 0 equals negative 3a, then negative 3a equals 1. A equals negative 1/3. And let's make sure the camera catches all that. So f of x is here, but a is now negative 1/3, so we just write this out with the negative 1/3. The minus minus becomes a plus, so we get x plus 1, and everything else is the same as what we have up there. And we've deduced the equation of the polynomial whose graph we see. And also gained the insight about what happens at a 0 that corresponds to a square of a linear factor like this.